part 284C3A. Line 22f1fa19c3a Affine sphere Diophantine geometry Faltings theory 5G Wow Seti. There's the alien radio signal there, and then Google affine sphere. Quotes from Wiki. In mathematics and especially differential geometry, an affine sphere is a hypersurface for which the affine normals all intersect in a single point. The term affine or affine sphere is used because they play an analogous role in affine differential geometry to that of ordinary spheres in Euclidean differential geometry. An affine sphere is called improper if all of the affine normals are constant. In that case, the intersection point mentioned above lies on the hyperplane at infinity. Affine spheres have been the subject of much investigation, which many hundreds of research articles devoted to their study. Google Diophantine geometry. Quotes from Wiki. In mathematics, Diophantine geometry is one approach to the theory of Diophantine equations, formulating questions about such equations in terms of algebraic geometry over a ground field K that is not algebraically closed, such as the field of rational numbers or a finite field, or a more general commutative ring, such as the integers. A single equation defines a hypersurface, and simultaneous Diophantine equations give rise to a general algebraic variety V over K. The typical question is about the nature of the set Vk of points on V with coordinates in K, and by means of height functions, quantitative questions about the size of these solutions may be posed, as well as the qualitative issues of whether any points exist, and if so, whether there are an infinite number. Given the geometric approach, the consideration of homogeneous equations and homogeneous coordinates is fundamental, for the same reasons that projective geometry is the dominant approach in algebraic geometry. Rational number solutions, therefore, are the primary consideration, but integral solutions, i.e. lattice points, can be treated in the same way as an affine variety may be considered inside a projective variety that has extra points at infinity. The general approach of Diophantine geometry is illustrated by Faltings' theorem, a conjecture of algebraic model starting that an algebraic curve C of genus G over 1 over the rational numbers has only infinitely many rational points. The first result of this kind may have been the theorem of Hilbert and Hurwitz dealing with the case G equals 0. The theory consists both of theorems and many conjectures and open questions. So I'm going to Google Faltings' theorem. Faltings' theorem from Wikipedia, the free encyclopedia in number theory. The Mordell conjecture is the conjecture made by Mordell in 1922 that a curve of genus greater than 1 over the field Q of rational numbers has only finitely many rational points. The conjecture was later generalized by replacing Q by a finite extension. It was proved by Jerd and Faltings 1983 and is now known as Faltings' theorem. July 19, 2012. My thoughts. There's the Q from the Wow signal 60QU5. Q in the equation, does it relate? Looking to see if it does. I always look for any keyword to see if it means something deeper. Faltings' theorem keyword is, let C be a non-singular algebraic curve of genus G over Q. Then the set of rational points on C may be determined as follows. Case G equals 0. No points or infinitely many. C is handled as a conic section. Case G equals 1. No points, or C is an elliptic curve, and its rational points form a finitely generated Albion group. Mordell's theorem, later generalized to the Mordell-Weil theorem. Moreover, Moser's torsion theorem restricts the structure of the torsion subgroup. Case G above 1, according to the Mordell conjecture, now Faltings' theorem, C has only a finite number of rational points. July 19, 2012. The keyword is conic section. It's going to be Googled in the next video. Okay?